What if the one constant that humanity has relied on since the dawn of modern physics, the speed of light, the ultimate cosmic speed limit, has not been constant at all? What if this fundamental pillar of our understanding, the number we trust, to measure distances across the stars and the ticking of cosmic clocks, has been quietly shifting ever so slightly since the very first heartbeat of the universe? Imagine for a moment that everything we have built our comprehension of reality upon the geometry of space, the flow of time, the unfolding of cosmic history rests on a foundation that might be moving beneath our feet. The consequences are staggering both scientifically and philosophically. It is not merely a question of numbers of meters per second, of formulas inscribed in textbooks. It is a question that reaches into the core of our perception, our sense of order, and the very nature of existence itself. How would we perceive our universe if the fabric of reality is subtly, persistently different from what we have always assumed? And more intriguingly, could we even recognize the truth if it has been slipping past us like a whisper in the wild dark? We are living in a universe where light, the most faithful messenger of information, the speediest courier of cosmic news, might be deceiving us. This is not a metaphor, nor a philosophical musing without consequence. Light governs everything we know about the cosmos. It sets the rhythm of time, the scale of space, and the very structure of matter. To imagine light as a trickster, bending its rules imperceptibly, is to challenge the foundation of modern physics itself. The speed of light, denoted as c, is more than a measurement. It is the heartbeat of the cosmos, the pulse by which the universe conducts its symphony of creation and evolution. And if that heartbeat has ever shifted, however minutely, the melody of everything we know, stars, galaxies, and even the tiniest particles dancing in the void, could be entirely different from what we have recorded, what we have measured, what we have assumed. Picture light as the rhythmic pulse of a giant cosmic heart beating through the expanse of space and time. Each pulse defines the distances between stars, the intervals that we call seconds, the very progression of causality. Imagine that pulse changing its pace imperceptibly over billions of years. One beat slightly faster, another fractionally slower, and suddenly the universe as we know it is transformed. The constellations, the distances to faraway galaxies, the very ticking of clocks across space might no longer correspond to reality. What appears stable, what seems eternal, might be an intricate illusion woven by the shifting cadence of light itself. It is an unsettling thought, one that invites a kind of quiet awe, a meditation on the fragility of knowledge and the subtle complexity of the cosmos. The implications of even the tiniest variation in the speed of light are profound. Measurements that astronomers take for granted, the calculations of distances to stars and galaxies, the inferred ages of cosmic structures, all rest upon c being immutable. If c were to drift, the cosmos would reveal itself differently through every telescope, every observation, every equation. Time itself, intimately linked with the speed of light through the laws of relativity, might stretch or compress in ways we cannot immediately perceive. Philosophically, this opens the door to questions that blend science with imagination. If both space and time are flexible, if the scaffolding of reality can bend with the subtle whims of light, are we truly experiencing an objective universe? Or are we navigating through a dreamscape shaped by the shifting pulse of the cosmos? Could it be that our understanding is merely a reflection, a shadow of the true rhythm of existence that has always eluded our grasp? Yet despite this potentially radical instability, there is something beautiful about contemplating such a universe. It is as if the cosmos itself is inviting us to step closer, to listen more intently, to pay attention to the whispers of photons traveling across billions of years. By considering the possibility that light has been changing since the Big Bang, we are forced to think not only about the mechanics of physics, but also about our place within that mechanics. We are reminded that knowledge is provisional, that certainty is rare, and that the universe may have hidden layers of meaning that we are only beginning to glimpse. There is both humility and wonder in recognizing that the constants we hold sacred might not be as steadfast as we believe. And in that uncertainty lies the thrill of exploration, the pull of curiosity, and the quiet, almost meditative joy of simply asking, what if? Let us step through this doorway together toward the first traces of light in the cosmos, and toward the ancient laws of physics that have guided our understanding for centuries. To embark on this journey is to follow the faint glow of photons that have traversed unimaginable distances, carrying with them the history of a universe in motion. We begin not with certainties, but with questions small and profound about the nature of reality itself. Consider the speed of light as the unchanging heartbeat of existence, a measure by which every event, every particle, every cosmic structure has been paced. Now imagine that heartbeat shifting imperceptibly, and you begin to see how fragile our assumptions truly are. Even the slightest deviation could ripple across time and space, altering our perception of everything from the formation of galaxies to the moments of history on our own planet. It is a gateway into mystery, a first step into a story that intertwines the tangible rigor of science with the boundless terrain of imagination. As we take this first step, consider for a moment how the universe might feel to someone living within a cosmos whose fundamental pulse is subtly, endlessly variable. It is a world both familiar and strange one, where every light year traveled is a journey not just across space, but through the shifting cadence of time itself. And yet in this strange universe there is a kind of quiet intimacy, an invitation to look deeper, to observe more closely, to ponder the elegance of a reality that is more complex and more beautiful than we could ever have anticipated. The story of the speed of light is not merely a scientific tale. It is a meditation on perception, on the limits of knowledge, and on the ever-present wonder of being able to ask, what if? And so we step forward, guided by light curiosity and the audacity to imagine a universe that has been quietly, inexorably changing around us since the very first moments of creation. Light does more than illuminate matter. It carries the story of the universe, tracing the passage of time and the structure of space with each photon that reaches our eyes or instruments. To understand the implications of a changing speed of light, we must first revisit the long and fascinating history of how humans have sought to measure, understand, and ultimately rely on this most fundamental messenger of reality. From the early curiosity of natural philosophers to the precision instruments of modern physics, light has served as both a guide and a challenge, shaping our understanding of the cosmos, while also reminding us how much we do not yet know. Imagine standing in the study of Isaac Newton in the quiet hours of the late 17th century, watching him contemplate prisms and the way sunlight splits into rainbows. Newton recognized that light was not merely a passive phenomenon, it was active, carrying information about the world and obeying the laws of nature in ways that could be described mathematically. He imagined a universe in which light was a particle, a stream of corpuscles racing across the void with consistency and purpose. To him, light was a tool, but also a key to unlocking the secrets of the heavens. It was in many ways the first step in humanity's attempt to quantify the immeasurable, to transform the ephemeral and intangible into something concrete and predictable. Decades later, James Clerk Maxwell elevated our understanding to a new level by showing that light is also an electromagnetic wave, a vibration of electric and magnetic fields propagating through space at a speed that could be calculated from known constants. Suddenly, light was no longer only a particle nor only a wave, but a bridge between forces, a carrier of information woven into the very fabric of physics itself. Maxwell's equations allowed humanity to predict the behavior of light, with unprecedented precision, turning photons into reliable messengers of cosmic truth. It is almost poetic to consider that light, this invisible courier, was revealing the deep symmetries of nature to anyone patient enough to follow its patterns. And yet, even as our understanding grew, so too did the mysteries. Light's constancy, its unwavering speed, became a cornerstone of physics, assumed to be immutable in all frames of reference. The very idea that c could vary would have seemed heretical, or at least wildly improbable to the giants who first wrote these equations. And yet, as we now allow ourselves to imagine, what if that cornerstone is not as solid as it once appeared? By the early 20th century, Albert Einstein would revolutionize our understanding of light and time. With his theory of special relativity, he demonstrated that the speed of light is not only central, but absolute, acting as a cosmic speed limit, unbreakable and universal. Space and time themselves were revealed to be malleable, stretching and contracting in accordance with the unyielding pace of light. Here the messenger and the message became inseparable. The rhythm of the universe was dictated by this very constant. Einstein's work not only changed physics, it altered the way humanity perceives reality. We were no longer just observers of the cosmos. We were participants in a dance choreographed by photons, traveling unfathomable distances at an unwavering speed. The elegance of this framework is undeniable, yet it relies entirely on the assumption that the speed of light remains exactly what we measure today. One slight variation, even imperceptible over eons, could shift our understanding of distance, time, and causality, altering the story of the cosmos from its earliest chapters to the present moment. Consider for a moment light as a messenger carrying news from the farthest reaches of space to our instruments here on Earth. Every star, every galaxy, every distant quasar communicates with us through the language of photons, and we interpret that language, assuming a steady, reliable courier. If the messenger changes speed even slightly, our interpretations could be profoundly skewed. Imagine reading a story in which the punctuation and sentence spacing subtly shifted with each line. The words would be the same, the letters familiar, yet the meaning could become warped, misaligned, or even entirely misleading. In the cosmic context, a changing speed of light would mean that the distances to galaxies might be misjudged, the ages of stars miscalculated, and the narrative of cosmic history rewritten without our knowing it. The stars would still shine, the galaxies would still rotate, but our comprehension of their motions and relationships could be fundamentally flawed. Every calculation, every observation predicated on the constancy of c, might carry hidden errors that only become apparent when we step back and ask the unorthodox question, what if light itself is not constant? The story of light is not merely about the technical achievements of physics. It is also a deeply human tale of curiosity, imagination, and humility. Every generation of scientists has relied upon the constancy of light, yet each also probes the boundaries of what is known. From measuring the time it takes for sunlight to reach Earth, to bouncing lasers off distant mirrors on the moon, to observing the ancient glow of the cosmic microwave background, humanity has continually sought to track the pulse of light across space and time. It is a pursuit that combines precision with wonder, calculation with awe, and it is precisely this duality that allows us to entertain the possibility that light may have its own history, a subtle evolution since the Big Bang that might be invisible to all but the most sensitive instruments and the boldest imaginations. As you follow this story, consider your own role as an observer, as someone who experiences the light of distant stars every night. The photons that enter your eyes have traveled millions, sometimes billions of years, carrying with them messages from a past you will never witness directly. Each particle is a tiny time capsule, a whisper from the cosmos, and we have learned to decode their signals with remarkable sophistication. Yet the question lingers: if the speed of these messengers has not been fixed, if their pace has shifted imperceptibly over cosmic time, how much of the story we read is true, and how much is a distorted echo? The implications stretch beyond physics into philosophy, challenging our assumptions about reality, causality, and the nature of truth itself. It invites us to hold our knowledge lightly, to marvel at what we know, and to remain open to the mysteries that light continues to reveal. Now, standing on the shoulders of Newton, Maxwell, and Einstein, we can appreciate the elegance of a universe interpreted through light, but we can also sense the fragility of that interpretation. The constancy of light has been our guiding principle, our cosmic ruler, Yet even the most faithful guides can change course over time. This brings us to the first critical question for our journey. How would we even measure the speed of light in the past across billions of years when the cosmos itself has evolved and shifted? How could we discern whether the messenger has altered its pace? And what would such a revelation mean for the grand narrative of space, time, and everything in between? As we move forward, we will trace the footprints of photons across the universe, examine the laws they obey, and confront the possibility that the story they carry may have subtle shifting threads that we have only just begun to detect. Each observation, each calculation becomes part of a larger tapestry, a dialogue between the known and the unknown, between what we see and what might truly be. And as we embark on this exploration, I invite you to imagine alongside me, to hold the universe in your mind, and to consider that light, the oldest storyteller of all, may have more to tell than we have yet dared to hear. It is almost impossible to overstate the trust humanity has placed in the constancy of light. For centuries, physicists and astronomers alike have assumed that the speed of light, denoted as c, is unchanging, an unwavering beacon guiding our understanding of space and time. Yet as we stand at the frontier of both observation and imagination, we must entertain a possibility that seems almost heretical: light may not be as faithful as we have always assumed. The idea is unsettling, not merely because it challenges the foundations of physics, but because it asks us to reconsider our very perception of the universe. What if the measurements and calculations we have relied upon for so long, from the distances to distant galaxies to the age of the universe itself, are slightly imperceptibly skewed by a messenger that has been subtly changing pace since the cosmos began? It is a question that feels at once improbable and deeply compelling, because the implications touch every corner of reality. The history of attempts to measure the speed of light is a story of human ingenuity, patience, and increasingly precise instrumentation. In the mid-19th century, the French physicist Hippolyte Fizeau made one of the first terrestrial measurements of c by using a rapidly rotating toothed wheel and a beam of light reflected from a distant mirror. Light racing across the distance and returning to the wheel allowed Fizeau to estimate its speed with remarkable accuracy for the time. Soon after, Léon Foucault refined these measurements using rotating mirrors, a method that improved both precision and confidence. These early experiments marked the beginning of an era in which light was quantified not as a mysterious phenomenon, but as a measurable, repeatable constant. Even then, scientists noticed subtle anomalies in different measurements, hints that the behavior of light might be more complex than previously imagined. By the 20th century, technology had advanced to allow measurements of extraordinary precision. Lasers, atomic clocks, and interferometers have since transformed the study of c from a pursuit of approximations to a quest for absolute exactness. Physicists could measure the speed of light to fractions of a meter per second, a level of precision that would have seemed magical to Newton or Maxwell. Yet paradoxically, the more we measured, the more questions arose. Observations of distant quasars, the polarization of light from faraway galaxies, and the redshift of cosmic objects hinted at subtle inconsistencies that defied straightforward explanation. These observations prompted a small but persistent subset of researchers to consider radical possibilities, including the notion that c itself might have undergone imperceptible shifts over billions of years. It is not that light is capricious in the ordinary sense, but that the very parameters we use to define it may not have been perfectly fixed since the Big Bang. The question of a varying speed of light also intersects with cosmology in ways that are both profound and perplexing. Consider the early universe, when matter and radiation were closely intertwined, a dense hot plasma in which photons were scattered, absorbed, and emitted continuously. In this primordial environment, even a minuscule change in the speed of light could have altered the way the universe expanded, how structures formed, and how energy propagated. Galaxies may have coalesced differently, the cosmic microwave background might carry subtle variations we have yet to detect, and the very timeline of cosmic history could be subtly distorted. The philosophical implications are equally profound. If light has changed speed over time, can we trust the story we infer from its journey across billions of years? Does the universe remember its own past? Or are we only glimpsing a version of events shaped by the evolving messenger that carries them to us? For an observer on Earth, this notion transforms the cosmos from a fixed stage into a dynamic narrative, one in which the tools we use to measure distances, durations, and velocities are themselves part of the story. Every photon arriving from a distant star becomes not just a message from the past, but also a record of its own passage, a subtle trace of the conditions through which it has traveled. When we calculate the age of a galaxy, or the speed at which it recedes, we are implicitly assuming that light has been constant throughout its journey. A small deviation from this assumption could reshape the entire cosmic map, altering our understanding of distances, timelines, and relationships between celestial objects. Imagine reading a historical chronicle in which the speed of ink drying changed unpredictably across the pages. The text might look familiar, yet the sequence of events could be misaligned. Light in this sense is the ink of the universe, and a varying sea would mean that our cosmic history is more interpretive than absolute. The scientific community approaches this idea cautiously, for it challenges the very pillars of physics established over centuries. Yet the possibility cannot be dismissed lightly. The pursuit of such questions has led to experiments examining ancient light, the fine structure, constant, and other cosmic markers, in an effort to detect even the faintest drift in C. By studying the spectral lines from distant quasars, researchers hope to detect minuscule shifts that could indicate a historical variation in light's speed. These studies, though subtle and technically demanding, open a doorway into a universe that is not as rigid as classical physics suggests. They invite us to view the cosmos not as a machine of unchanging gears, but as a living, evolving entity, one in which even the most sacred constants might breathe with the passage of time. As you consider this, try to feel the subtle tension between certainty and possibility, between what is measured and what might be. We often take for granted the notion that the speed of light is fixed, that space and time provide a consistent stage upon which cosmic events unfold. Yet the very same light that illuminates the universe also challenges our assumptions. By contemplating a scenario in which C has shifted, we are invited to imagine a cosmos that is simultaneously familiar and alien, one in which history might be slightly out of sync with our observations. The idea carries a meditative quality, prompting us to step back and acknowledge the limits of perception while marveling at the elegance of the natural world. It is a reminder that science is not merely a collection of facts, but a dynamic process of questioning, refining, and reimagining reality. In this context, even the smallest potential variation in C is not just a technical curiosity, but a philosophical invitation. It asks us to consider the nature of time, the reliability of observation, and the fragile scaffolding upon which we construct knowledge. Each photon arriving from distant galaxies is a fragment of history, a witness to the unfolding of the universe. And if those photons have traveled at a subtly changing pace, the story they tell may be one that differs in tone or emphasis from the one we have assumed. There is a profound beauty in this uncertainty, an elegance in realizing that the cosmos may be more intricate and dynamic than our most precise instruments can fully capture. To wonder if light itself is not constant is to engage with the universe in a way that is both deeply intellectual and profoundly human, blending curiosity with humility, measurement with imagination. And so, standing on this threshold, we are compelled to seek the traces of light that might reveal its historical behavior. The question moves us from terrestrial laboratories to the far reaches of space, to ancient photons that have traveled billions of years across an expanding universe. To investigate whether light has changed, we must examine the immutable records left behind in the form of particles and radiation, the subtle signatures embedded in the cosmic microwave background, and the interactions of light with matter at extreme distances. It is a journey that requires patience, precision, and imagination, a journey that blurs the boundary between observer and observed past and present. Each experiment, each observation becomes a dialogue with the universe itself, a chance to read the story encoded in photons while questioning the fidelity of the messenger. In following these traces, we prepare to step further into the cosmic past, toward the very fabric of reality, and toward the photons that have quietly borne witness to everything since the beginning of time. Every particle of light carries with it a story, a fragment of the universe's memory, a whisper from eons past. Each photon is not simply a point of energy traveling through space. It is a messenger, a traveler, from a distant corner of the cosmos, bridging unimaginable expanses to deliver information that allows us to reconstruct the history of everything we see. When you gaze at the stars, what your eyes capture is not only illumination, but a narrative woven over billions of years, a chronicle encoded in the subtle oscillations and wavelengths of light. These tiny particles, invisible to the naked eye until they interact with matter, are the threads from which the vast tapestry of the universe is embroidered. They tell of collisions and explosions, of the birth of stars and galaxies, of processes that occurred long before Earth, long before life, long before consciousness itself emerged to witness them. And yet, if the speed at which these messengers travel is not absolute, the stories they carry might be subtly, profoundly altered. Photons, in their elegant simplicity, behave as both particles and waves, a duality that has fascinated physicists for over a century. They are simultaneously precise carriers of energy and frequency, and rippling undulations capable of interference and diffraction. This duality allows photons to serve as incredibly versatile messengers, conveying information about the universe in multiple dimensions. Imagine each photon as a small, steadfast spacecraft, launched from a distant star or galaxy, hurtling across the void to reach your instruments here on Earth. Its mission is to report the conditions from its point of origin, revealing the temperature, composition, and motion of celestial objects. The journey is long and perilous, spanning billions of light years, yet the photon remains remarkably faithful, obeying the laws of physics and preserving the integrity of the information it carries. And yet, what if the very velocity that determines the duration and trajectory of its voyage has shifted even imperceptibly over cosmic time? If photons have traveled at variable speeds, even minutely, our interpretations of the universe could be flawed in ways we are only beginning to imagine. Astronomers calculate distances to stars and galaxies, estimate the ages of celestial objects, and reconstruct the sequence of cosmic events based on the assumption that light has moved at a fixed rate. Each piece of information is essentially a time capsule, the age of the photon corresponding to a snapshot of the universe when it first departed its source. Now consider that the messenger may have altered its pace. The distances we measure may be slightly inaccurate. The timing of events subtly distorted, the history of galaxies and clusters misaligned. The universe we read is a version filtered through the journey of photons, and any variation in that journey introduces a layer of uncertainty into the story. What appears to be a well-ordered, coherent cosmos might be slightly shifted, like reading a chronicle where the sentences have been reordered or stretched without our noticing. This notion is both humbling and thrilling. It invites us to think of light not merely as a neutral courier, but as an active participant in the cosmic narrative. Photons are not just passive carriers of information, they are entwined with the structure of space-time itself. In quantum mechanics, each photon embodies probabilities, interactions, and entanglements, subtly reflecting the environment through which it has passed. This means that the journey of a photon is not just a measurement of distance, but a dialogue between itself and the cosmos, recording minute influences of gravity, electromagnetic fields, and even the expansion of space. If the speed of light has fluctuated, these dialogues would contain echoes of change, whispering secrets about the evolving nature of the universe that we have yet to fully decipher. It is a reminder that the universe is not a static stage, but a dynamic interplay, where messengers and message are inseparable, and every observation carries within it both clarity and ambiguity. To visualize this, imagine a single photon leaving a star billions of years ago. It begins its journey in a region where the laws of physics are similar yet subtly different from what we observe today. Perhaps the local density of space-time affects the photon's speed, or some cosmological process in the early universe caused minuscule variations in how light propagated. The photon travels encountering galaxies, black holes, and interstellar matter, all the while carrying encoded information about the time and place of its origin. By the time it arrives at Earth, we interpret it using the assumption that its speed has been constant. We measure its wavelength, its energy, its frequency, and from these data points reconstruct a picture of the universe at a distant epoch. But if the photon's velocity has not been fixed, our reconstruction is a slightly distorted image, like looking through a lens that subtly warps the dimensions without our noticing. The farther the journey, the greater the potential distortion, and the more challenging it becomes to discern the original message accurately. This is why understanding the behavior of photons over cosmic time is not just an academic exercise. It is essential to building an accurate map of the universe. The philosophical implications of this are profound. When we depend on light to tell the story of the cosmos, we implicitly trust that the messenger has been reliable. But if there is even a small, undetected variability in its speed, the universe we perceive may be a reconstruction of events rather than a precise record. We might be reading a memoir with blurred pages, a chronicle in which the sequence of events is approximate rather than absolute. This invites a sense of awe and a recognition of humility. We are privileged observers, yet our tools and perceptions are limited. The universe may remember its past differently than we perceive, and photons in their dual role as particles and waves may be offering us an account that is simultaneously accurate and subtly altered. There is beauty in this ambiguity, a poetic tension between certainty and mystery that makes the act of observation itself a deeply contemplative experience. As we examine the cosmos through the lens of photons, we begin to appreciate the complexity of the information they carry. Every interaction a photon experiences leaves a trace, a fingerprint of its journey. Gravitational lensing bends its path. Cosmic expansion stretches its wavelength, and encounters with interstellar matter alter its properties in subtle ways. These effects are well studied, yet they also underscore how sensitive our measurements are to the fundamental assumptions we make about light. If the speed of light has drifted over time, these traces become more than mere curiosities. They are the keys to understanding a deeper story about the evolution of the universe itself. Each photon is thus both a messenger and a puzzle, a tangible particle traveling through the void while simultaneously encoding a complex layered history. It is as if every photon is whispering, inviting us to decode the subtle rhythms and patterns of a cosmos that is both ordered and fluid, precise and mysterious. And so we arrive at a point of reflection. Each photon is a fragment of memory, a traveler bearing witness to cosmic history, and yet, like all travelers, its path and pace may have shifted imperceptibly over eons. This possibility challenges our assumptions and deepens our appreciation for the delicacy of our observations. The universe is vast, intricate, and at times almost poetic in the way it communicates through light. To contemplate photons as both storytellers and participants in cosmic evolution is to engage in an act of curiosity that blends science, philosophy, and imagination. Every measurement, every telescope image, every spectrum is part of a conversation with these ancient messengers, and by listening carefully, we may begin to discern whether the rhythm of their journey has ever changed. As we continue, it becomes essential to view light not simply as a tool for measurement, but through the lens of time and space itself, recognizing that photons are intimately tied to the very structure they traverse. Only by understanding the interplay between light, time, and space can we begin to unravel the subtleties of the universe, and perhaps glimpse the profound ways in which a varying speed of light could shape our perception of everything from star formation to the history of galaxies. In this way, light is not just illumination, it is memory history and a guide through the boundless landscape of the cosmos, inviting us to follow, question, and imagine. Time is often perceived as the most reliable constant, a steady, unyielding arrow moving from past to future, an invisible metronome by which we measure our lives and the cosmos alike. Yet the relationship between light and time, as revealed by Einstein's theory of relativity, suggests that this arrow is not as rigid as intuition might have us believe. The speed of light is not merely a measurement of distance over duration. It is the connective tissue that binds space and time into a coherent, interwoven fabric. Alter the speed of light even slightly, and the rhythm of this fabric shifts, bending, stretching, or compressing in ways that defy everyday experience. Imagine a river wide and steady flowing with gentle persistence. In this metaphor, the water represents time itself, while the current is determined by the passage of light. If the flow of light were to accelerate, the river would surge, carrying everything downstream more rapidly. If it were to slow, time itself would pool, dilate, and stretch across the landscape. The topography of the universe as we perceive it depends intimately on the pace of this river, and even subtle changes could transform the scenery entirely. In relativity, time is not an absolute entity, but a variable intertwined with space and velocity. Clocks moving at different speeds relative to one another measure time differently, a phenomenon verified in countless experiments from atomic clocks on fast-moving aircraft to satellites orbiting the Earth. Light establishes the maximum speed at which information can travel, and it is this ceiling that defines simultaneity, causality, and the very order of events. Without a fixed speed for light, the concept of a universal timeline begins to unravel. A photon traveling across the universe is not merely moving through empty space. It is threading together the sequence of events in the cosmos. Alter its velocity, and the ordering of those events could subtly shift. What seems linear to an observer in one region of space may have unfolded differently elsewhere, and the seeming inevitability of cause and effect may be more a product of the photon's journey than an absolute property of reality. Consider for a moment a distant star whose light has traveled billions of years to reach our telescopes. We measure its age, its distance, its velocity based on the assumption that c has been constant throughout the journey. Each calculation is a reconstruction, an extrapolation backward in time, from a photon that carries a snapshot of its source. If the speed of that photon varied during its passage, even imperceptibly, the chronology we infer could be subtly distorted. The star might have formed slightly earlier or later than we believe, its surrounding environment slightly different, and the history of its galaxy altered in ways our instruments cannot detect directly. In this sense, time is not a fixed conveyor belt of events, but a fluid landscape shaped by the very light that illuminates it. The metaphor of water is apt. The river of time is guided by the currents of light, and the flow of these currents determines how we perceive the sequence of events in the universe. The philosophical implications of this are profound. If time is flexible, if its apparent linearity is partially a product of light's behavior, then our understanding of history, causality, and even existence itself is less secure than we imagine. We tend to think of past, present, and future as distinct layers, a tidy continuum stretching from the Big Bang to now. Yet the universe may be more like a complex painting in which the brushstrokes are smeared and layered, shaped by the tools used to perceive it. Light as the painter's medium determines not only what we see, but also how we interpret the passage of events. Change the medium slightly, and the entire composition can shift in tone, in texture, in the sequence of visible patterns. This invites us to question the fundamental nature of time. Is it truly linear, or is linearity an emergent illusion created by the interplay between light, space, and perception? Could our subjective experience of sequential events be a morting reflection of the constraints imposed by photons traveling through a dynamic, evolving universe, rather than a direct representation of an objective temporal order? Moreover, the early universe, dense, hot, and rapidly expanding, magnifies the potential consequences of any variability in the speed of light. In the first moments after the Big Bang, light was intimately coupled with matter and radiation, influencing how the universe expanded and cooled. Tiny fluctuations in the velocity of photons during these critical phases could have altered the formation of large-scale structures, the synthesis of elements, and the distribution of energy across space. The river of time carrying the unfolding of cosmic events might have flowed differently in those early epochs, producing a cosmos that looks familiar yet is subtly divergent from what we reconstruct today. Each galaxy, each cluster of stars, and each cosmic void may thus contain the echoes of time shaped not only by expansion and gravity, but by the rhythm of light itself. Our perception of order of historical sequence may be a narrative crafted in part by the pace of photons stretching across the cosmic river. There is also a psychological resonance to this idea, for it challenges the comforting notion of a fixed chronology. We construct our lives and our understanding of the universe around the assumption that time is reliable, predictable, and universal. Yet relativity, quantum mechanics, and now the possibility of a changing speed of light suggest that this assumption is provisional. Time, as experienced by conscious observers, may be a localized phenomenon dependent on the flow of light, the curvature of space, and the specific paths that information takes across the cosmos. The universe may contain regions where events appear to unfold at different rates, where histories diverge subtly from the trajectories we expect, and where the past is not a single immutable record, but a flexible dynamic canvas. In this context, every photon is a chronographer, every measurement a potential distortion, and every observation an opportunity to re-examine the nature of temporal reality. To imagine time in this way is to cultivate both humility and wonder. It is to recognize that the arrow of time, which seems so obvious in our daily lives, may be more malleable than the centuries of observation and theory suggest. Each photon, each beam of light not only illuminates space, but also encodes temporal information carrying with it the sequence of events as filtered through its own journey. Alter the speed of light and the rhythm of this journey changes with cascading effects that may ripple through the entire cosmic timeline. This invites us to consider the universe not as a static chronicle of events, but as a dynamic interplay of perception to measurement and reality, in which time itself is a fluid participant, guided by the flow of photons across the expanse of space. And so as we contemplate the flexibility of time, we are drawn to reimagine the earliest moments of the cosmos. The universe in its infancy may have experienced a rhythm of temporal unfolding markedly different from our conventional expectations. The processes that seeded galaxies, forged the first stars, and distributed matter and energy across space may have done so in a context where the pace of time itself was influenced by the subtle behavior of light. The early cosmic river, like water, encountering unseen eddies and currents, may have carried the flow of events along paths that deviate from our present reconstructions. Each observation of ancient light is thus an invitation to ponder not only the objects and structures we see, but the temporal dynamics that shaped their emergence, and the hidden interplay between photons and the flow of time that frames the unfolding story of the universe. The first second of the universe was not merely a moment, it was a crescendo of creation, a burst of energy and potential so intense that our minds struggle to grasp it. In that initial instant, the universe expanded from an incomprehensibly dense, hot singularity into something that would eventually give rise to galaxies, stars, planets, and life itself. Light in those fleeting moments was more than illumination. It was a participant, a dancer entwined with matter, in a cosmic choreography that defined the very fabric of reality. The speed at which light moved during this embryonic phase, the value of C dictated how quickly interactions could propagate, how energy could disperse, and how the first structures could begin to emerge from the chaos. Imagine the universe as a vast canvas suddenly set ablaze with light and matter, each photon racing across the newborn cosmos, transferring information, shaping energy fields, and establishing patterns that would ripple across time. Every subtle shift in the pace of those photons could have altered the unfolding of events, creating a universe that is in some ways familiar yet subtly different from what we reconstruct today. In the earliest microseconds, the cosmos was a maelstrom of activity. Temperatures soared to unimaginable levels. Particles collided with furious energy, and radiation dominated the scene, carrying energy and information at the speed of light. Matter and energy were so intertwined that they performed a complex coordinated dance. Photons bounced, scattered, and interacted incessantly with primordial particles. This was a universe in motion, dynamic and fluid, where light was both messenger and mediator, shaping the flow of events even as it traveled through them. If the speed of light had been slightly higher, photons might have traversed the expanding space more quickly, facilitating different rates of particle interaction and cooling. If it had been slower, the rhythm of these processes would have lagged, possibly delaying the formation of the first atomic nuclei, the first neutral atoms, and the earliest structures that seeded galaxies. The delicate interplay between light and matter in those first seconds set the stage for everything that followed, a subtle ballet that determined the architecture of the cosmos for billions of years to come. To envision this picture, the universe not as a static void, but as a rapidly unfurling tapestry, threads of energy and matter intertwining in real time. Light is the golden filament weaving through this tapestry, transmitting information, pacing interactions, and subtly guiding the structure of reality itself. In this vision, each photon carries with it the potential to influence the universe's trajectory. A minuscule variation in the velocity of these early photons would ripple outward, altering the timing of interactions, the temperature distribution, and the growth of fluctuations in density that would eventually form stars and galaxies. These fluctuations, tiny differences in the concentration of matter, are the seeds from which all large-scale structures grow. Altering the speed of light even marginally could change the weight and arrangement of these seeds, producing a universe that, while recognizable, is in essence a slightly edited version of what might have been. We may be witnessing not the universe as it occurred, but a reconstruction shaped by the very messenger through which we perceive it. The notion that the laws of physics themselves could have behaved differently in those earliest instants is both provocative and disorienting. Constants that we take for granted today, gravitational relationships, electromagnetic interactions, thermodynamic behavior, were all contingent on the speed of light. If c were higher or lower, the strength of these interactions, the propagation of forces, and the evolution of energy distributions could have been subtly altered. This raises a profound question. Are we observing the universe as it truly existed, or are we interpreting a version edited by the historical behavior of photons? Each observation of distant galaxies, each measurement of primordial elements, each detection of cosmic radiation is filtered through light that has traveled for billions of years. If that light's speed has not been constant, we may be looking at a universe whose story is partially refracted, a version of reality that reflects the messenger as much as the events themselves. The implications are staggering. Our models of cosmic history, while extraordinarily detailed and predictive, may contain hidden contingencies, subtle distortions that we have yet to detect. This possibility also challenges our sense of temporal immediacy and causality. In the first seconds after the Big Bang, the universe was expanding at a tremendous rate, and light was threading through this rapidly inflating space. Any variation in speed would have adjusted the synchronization of events, influencing how quickly regions of the universe could communicate, how energy equilibrated across vast distances, and how the first signs of structure emerged from uniform chaos. The universe we observe today, with its galaxies neatly arranged in clusters and filaments, may have crystallized in a pattern that reflects not only fundamental physics, but also the historical behavior of light itself. We are observers peering through a lens shaped by both space-time and the travel of photons, a lens that may subtly warp the sequence of cosmic events. The distinction between the actual early universe and the reconstructed narrative we perceive may be more nuanced, more delicate than we have assumed. Philosophically, this invites reflection on the nature of observation and reality. Photons are our earliest witnesses, our most reliable sources of information, yet they carry with them the possibility of subtle alteration. In a sense, we are reading a manuscript whose pages were written in motion, whose letters may have shifted slightly, as the ink dried across an expanding universe. The story is legible, coherent, even beautiful, yet we must recognize the possibility that it is not unaltered. Each photon from the first seconds of the cosmos is both reporter and participant, encoding in its wavelength energy and trajectory the conditions of its origin, while also reflecting the historical medium through which it has traveled. Understanding the first second of the universe thus requires not only physics and mathematics, but a willingness to entertain subtle uncertainties, a recognition that the universe we reconstruct is filtered through the medium of light itself. This perspective casts the cosmic microwave background, the faint afterglow of the Big Bang, in a new light. These ancient photons have traveled for over 13 billion years, carrying a map of the early universe imprinted upon their energy and polarization. If C varied even slightly in the earliest moments, the patterns encoded in this background radiation could reflect not only the distribution of matter and energy, but also the historical behavior of light itself. Every fluctuation, every temperature anisotropy becomes a piece of a puzzle that might be slightly skewed, an account of the universe filtered through a subtly evolving messenger. In this way, the first second after the Big Bang is both a foundation and a mystery, a moment of creation that established everything that followed, yet one whose details may remain partially veiled, accessible only through careful observation, creative interpretation, and the recognition that light itself may have been changing its pace as the universe unfolded. And so, as we contemplate that singular, intense first second, we are compelled to follow the traces left behind, the enduring signatures of the earliest light. We seek to understand how photons born in the furnace of creation carry the echoes of those initial interactions, and whether their speed has remained steadfast or subtly shifted over cosmic time. The implications extend far beyond the first second itself, shaping our perception of every star, every galaxy, every cosmic event that we observe today. To explore this further, we must examine the cosmic relics left behind, the faint, omnipresent radiation that pervades all of space, the afterglow of the universe's first heartbeat, and through it seek to discern the story written in the very first photons, the story of the universe in its most formative, fleeting moments. Every photon in the cosmic microwave background carries with it a signature of the universe's earliest moments, a delicate imprint from a time when the cosmos was young, dense, and roiling with energy. This ancient light, stretched and cooled over more than 13 billion years, forms a tapestry that scientists have come to rely on as a primary record of the universe's infancy. Known as the cosmic microwave background, or CMB, this radiation is a relic of the hot plasma that filled the cosmos shortly after the Big Bang. It is a pervasive, almost uniform glow that envelopes the entire sky, a faint whisper from the past that reveals the temperature, density, and composition of the universe at the time of its release. Each photon is a messenger from a time when the universe was less than 4,000,000 years old, and together they form a remarkable historical record. Yet as we consider the possibility that the speed of light may not have been perfectly constant, the clarity of this record comes into question. How reliable is the CMB? If the messenger itself, the photon, has subtly changed its pace during the journey across space and time. To understand the significance of the CMB, imagine it as a photograph of the universe at its earliest stage. A snapshot capturing the intricate patterns of temperature fluctuations that would later seed the formation of galaxies and large-scale structures. These fluctuations are tiny, mere fractions of a degree in temperature, yet they encode the blueprint of cosmic evolution. Scientists study these patterns to infer fundamental properties of the universe, including its age rate of expansion and the relative distribution of matter and energy. It is a profound achievement, allowing humanity to peer back across billions of years to reconstruct events that occurred long before Earth existed. But this reconstruction relies critically on the assumption that the speed of light, the pace at which these photons traveled, has remained consistent. If c has varied even slightly, The spatial and temporal mapping inferred from the CMB could be distorted like a photograph taken with a lens that subtly stretches or compresses the scene. Consider what such a distortion might entail. Astronomers measure the angular size of fluctuations in the CMB to estimate the scale of structures in the early universe. They rely on the speed of light to convert these angular measurements into physical distances and from there to model the timeline of cosmic history. If the speed of light were faster in the early universe, the photons would have traveled farther in the same amount of time, potentially making regions of space appear closer than they actually were. Conversely, if light were slower, distances could be overestimated. This would have cascading effects on our understanding of galaxy formation, the expansion rate of the universe, and even the inferred age of the cosmos. The picture we take for granted, the elegant, almost static map of the infant universe, could be subtly altered by the very medium through which we interpret it. What seems precise and absolute may in fact be a reconstruction filtered through the historical behavior of light itself. The CMB also provides a unique window into fundamental physics because it encodes information about interactions between photons and matter in the primordial plasma. Tiny imbalances in temperature and density left imprints that can be read as signatures of the laws governing the early universe. If the speed of light has shifted over time, these signatures may be slightly misinterpreted. Physical constants derived from these observations, like the fine structure constant, could appear different than they truly were. Even subtle variations in C could lead scientists to conclude, for instance, that the universe expanded at a slightly different rate than it actually did, or that certain processes occurred earlier or later than in reality. The consequences are both technical and philosophical. We rely on light not just to illuminate objects in space, but to illuminate history itself. Yet, the reliability of that illumination may be subtly compromised by the evolution of the messenger. This realization invites a reconsideration of what we mean when we speak of the age and scale of the universe. The CMB is often described as the oldest light in the universe, a nearly uniform background against which cosmic history is measured. But if the velocity of photons has varied, we are essentially reading a historical manuscript whose page lengths may have subtly shifted over time. The events we reconstruct, the epochs we define, and the distances we calculate could all carry hidden distortions. Imagine studying a tree ring record where the spacing of rings changed not only due to growth conditions, but also because the medium of measurement itself was subtly stretching. Our interpretation of the tree's age and the environmental conditions it experienced would be skewed. Similarly, the CMB serves as our cosmic dendrochronology, but one filtered through photons that may not have always traveled at the same pace. Furthermore, this scenario highlights the intimate interplay between observation and interpretation. Photons in the CMB are both witnesses to the early universe and participants in the transmission of information. Their journey across expanding space is shaped by gravitational influences, interactions with matter, and the possible historical evolution of their own properties. To study them is to engage in a delicate act of translation, decoding patterns that have traveled billions of years and may carry subtle signatures of change. The very assumption that C is constant underpins this translation. If that assumption is loosened, our understanding of the CMB, and by extension the entire cosmic timeline, requires careful re-examination. Each fluctuation in the background radiation, each tiny anisotropy, becomes a window not only into the past, but into the nature of the light itself and the subtle history it has borne. This consideration also invites philosophical reflection on the nature of evidence and reality. The CMB is more than data. It is a conversation with the universe, a record of its earliest heartbeat, a witness to creation itself. If the messengers of that record, photons, have changed their pace over time, our interpretation becomes an act of informed inference, a dialogue between what is observed and what may have occurred. The universe does not come to us fully packaged. It is filtered through the medium of light, and any historical variability in that medium introduces nuance, ambiguity, and the need for careful interpretation. It reminds us that scientific knowledge, while extraordinarily powerful and predictive, is contingent upon the fidelity of the information we receive and the assumptions we bring to its analysis. As we consider the cosmic microwave background in this light, we begin to recognize its dual role. It is both a map of the early universe and a subtle record of the messenger itself. The distribution of temperature fluctuations, the polarization patterns, and the minutiae of energy density are all influenced not only by the physics of the primordial cosmos, but by the historical behavior of light across cosmic time. Even small changes in C could lead us to misread the distances between structures, the age of the universe, or the chronology of galaxy formation. Each photon is therefore both a storyteller and a participant, encoding a narrative that is inextricably tied to its own journey. This understanding sets the stage for a broader inquiry. If the speed of light has potentially varied over cosmic time, what does that mean for other fundamental constants that underpin physics? The CMB provides one of the most detailed and sensitive probes we have, allowing scientists to test the stability of constants, like the fine structure constant and the ratios of particle masses. If C were not fixed, might other constants also have evolved? How would that influence our understanding of the laws governing chemistry, nuclear reactions, and the formation of stars and planets? By examining the relic radiation from the early universe, we are not only mapping its history, but probing the deeper question of whether the bedrock principles of physics are themselves truly constant, or if the cosmos contains subtle, evolving rhythms that have shaped reality from the very beginning. The universe as we understand it is built upon a delicate network of constant quantities that seem steadfast and immutable, underpinning the laws of physics that govern everything from the motion of planets to the fusion in stars. Among these, the speed of light c holds a particularly central position, linking space, time, energy, and matter in an elegant dance of equations. But c does not exist in isolation. It shares the stage with other fundamental constants. Planck's constant h, which dictates the scale of quantum behavior, the gravitational constant g, which governs the pull of matter across space, and the fine structure constant alpha, which determines the strength of electromagnetic interactions. These constants are woven together into the tapestry of the cosmos, each one a thread whose tension and tone contribute to the symphony of reality. And here lies the intriguing, almost unsettling thought: if the speed of light has shifted over cosmic time, even slightly, the other constants may not have remained immune. Imagine for a moment the universe as a grand instrument, a celestial harp with many strings. Each fundamental constant is a string producing a specific tone, a vibration that shapes the way the universe behaves. The speed of light is a primary string, the one that sets the key, the underlying rhythm of the orchestra. If this string stretches or tightens, the harmonies produced by the other strings inevitably change, altering the music. A change in C might subtly shift the rhythm of electromagnetic interactions, adjust the spacing of quantum energy levels, or modify the balance of gravitational forces that sculpt galaxies. The consequences are profound. Physics, which we often treat as the universal language of nature, may be less a fixed lexicon and more a mutable composition sensitive to the conditions of the medium through which it is expressed. Consider Planck's constant h, which dictates the granularity of energy in quantum systems. It is intertwined with c in the very definition of energy and momentum. If c has varied, the effective behavior of h could shift, correspondingly altering the structure of atoms, the frequencies of spectral lines, and the energies of photons emitted or absorbed by matter. Gravitational interactions governed by g might also respond indirectly, since the curvature of spacetime in relativity is tied to the interplay between mass energy and the speed at which information propagates. Electromagnetic forces modulated by the fine structure constant alpha would experience a corresponding change, since alpha is proportional to the square of the elementary charge and inversely related to Planck's constant in c. A subtle alteration in C can ripple across this network, subtly changing the rules of the game by which matter interacts, energy transfers, and structures emerge. The universe, which appears orderly and predictable to us, could be a melody whose underlying key has shifted over billions of years. This idea challenges the deeply ingrained notion that physics is a universal, immutable language. We often think of the constants as the grammar of nature, the punctuation marks that allow equations to reliably describe phenomena everywhere, at every time. If they are in fact subject to change, our models may be more approximate than we imagine, capturing patterns with remarkable accuracy, yet missing subtle nuances introduced by evolving constants. Observations that seem precise, such as the spectral lines from distant galaxies or the ratios of isotopes in ancient stars, could carry hidden adjustments shaped by the historical behavior of C and its companions. In essence, we may be reading a text whose punctuation subtly shifted as the ink dried, interpreting events with a fidelity that is extraordinary yet not absolute. To grasp the scale of this possibility, consider the fine structure constant alpha, which governs the strength of electromagnetic interactions. Small variations in alpha over cosmic time could influence atomic structures, chemical reactions, and the emission or absorption of light by matter. The cosmos would not collapse or explode from such changes. The laws of physics would still function, but the detailed behavior of matter could diverge from our expectations. Stars might burn at slightly different rates, elemental abundances could shift, and the spectra we rely upon to measure cosmic distances and ages could carry hidden distortions. Every observation, every model, every conclusion drawn about the structure and history of the universe would be filtered through this dynamic network of constants. Raising the profound question, is the physics we observe truly timeless, or is it a snapshot of an evolving set of parameters that have been subtly modulated across the aeons? Planck units, those elegant natural units derived from H, G, and C, provide a particularly striking example. They define scales of length, time, and mass that are meant to be universal, intrinsic to the fabric of reality itself. But if C is mutable, the Planck length and time, the fundamental yardsticks by which we measure the quantum structure of space, and the earliest instance of the cosmos might shift accordingly. The very scales that define the bridge between quantum mechanics and general relativity could fluctuate, hinting at a universe whose architecture is subtly dynamic, not fixed. The constants, which we often treat as immutable coordinates on the map of reality, may instead be part of a landscape in motion, evolving slowly, imperceptibly, yet profoundly over cosmic history. This perspective also carries philosophical weight. If constants can change, the notion of absolute truth in physics becomes more nuanced. The laws of nature may be robust and consistent within local domains, yet contingent when viewed across vast stretches of space and time. We are observers embedded in a universe whose score we read as if frozen, yet whose harmonics may have shifted during the performance. The elegance and precision of physical laws are not diminished. Rather, they acquire an additional layer of wonder, a recognition that the cosmos is both reliable and dynamic, structured and fluid, predictable and yet subtly surprising. It invites humility, a reminder that our understanding, however sophisticated, is always provisional, always filtered through the instruments and messengers at our disposal, and shaped by the very constants we assume to be unchanging. Furthermore, the interconnectedness of constants implies that the universe is a finely tuned system. Small variations in one constant are not isolated, they reverberate through the network, adjusting the behavior of others. This interdependence suggests that even minor changes in C could produce a cascade of subtle effects, shaping chemistry, star formation, nuclear processes, and the evolution of galaxies. The cosmic narrative, as reconstructed through observation and theory, might therefore reflect a universe that has adapted its own rules over time, a universe in which the laws we consider eternal are in fact entwined with the historical behavior of the fundamental quantities that define reality. As we contemplate this, the analogy of music returns. Imagine a symphony in which a single string subtly stretches during the performance. The entire harmony shifts, the timbre and resonance of each instrument subtly altered, yet the overall structure remains recognizable. Similarly, the universe could evolve in a way that maintains coherence, while the underlying constants, its strings and notes, experience gentle historical modulation. The resulting reality is both familiar and slightly altered. A universe whose apparent precision carries within it the memory of change. A record encoded in the messengers of light, the relics of the cosmic past, and the interconnected web, constants that govern all interactions. And so, as we move from the cosmic microwave background to the consideration of fundamental constants, we see a universe that may be less rigid than it appears. If the speed of light is mutable, the other constants may dance in response, creating a dynamic symphony of physics in which time, space, energy, and matter are intimately linked. This possibility opens the door to imagining consequences on a cosmic scale where the evolution of constants could subtly shape the architecture of galaxies, the formation of stars, and the flow of cosmic history itself. The next step in this contemplation is to expand the lens, to consider the universe on the largest scales, and to ask how a symphony of shifting constants might play out across the vast theatre of space-time. Imagine peering through a telescope at a galaxy, millions or even billions of light-years away. Every point of light, every glimmer, is a message sent long before our planet even existed, traversing the vast expanse of space at the speed of light. We have long relied on C as the cosmic yardstick, the ultimate ruler by which distances, velocities, and the scale of the universe are measured. But if the speed of light is not as constant as we assume, this fundamental measurement tool becomes more like a flexible tape measure, subtly stretching or contracting as we attempt to map the cosmos. The implications are profound, reshaping our understanding of how far galaxies lie, how quickly they move, and even how old the universe is. Every estimate of distance becomes contingent. Every calculation of cosmic expansion carries an uncertainty rooted not in observational error, but in the historical behavior of light itself. Think of light as a ruler forged at the dawn of the cosmos, one that spans unimaginable distances. We point it across space and it gives us numbers millions, billions of light years. Yet, unlike a rigid wooden yardstick, this ruler might have been malleable, bending subtly over time. A photon emitted from a distant galaxy did not necessarily traverse space at the same pace throughout its journey. If C were slightly faster in the past, that galaxy could be closer than we infer. If slower, it could be farther. These are not trivial adjustments. A few percent difference in light speed across billions of years could shift our estimates of galactic distances by millions of light years, altering the perceived scale of cosmic structures and the relationships between clusters, voids. The familiar tapestry of the night sky with its neatly plotted galaxies and filaments could be subtly warped like an image projected through a lens with an evolving focal length. Astronomers also use light to gauge the velocity of galaxies, relying on redshift, the stretching of light waves as space itself expands. Redshift is interpreted as a combination of recession, velocity, and distance, an intricate dance between motion and the expansion of the universe. If the speed of light varies over time, the relationship between observed redshift and actual distance becomes more complex. A galaxy's apparent speed could be misjudged, its motion either exaggerated or understated, depending on the historical pace of photons. The Hubble constant, that celebrated measure of the universe's expansion rate, could be subtly off, reflecting not only the dynamics of space-time, but the evolving nature of light itself. Every chart, every map, every cosmological model derived from these measurements carries the implicit assumption that C is fixed. If this assumption is loosened, the entire cosmic narrative may need reinterpretation, to a reminder that our understanding of scale and movement is inseparable from the behavior of the messengers that convey it. The philosophical consequences are equally compelling. If the distances we measure are contingent on the properties of light, are we truly comprehending the universe as it exists, or merely reconstructing a version filtered through the journey of photons? the galaxies we catalogue, the structures we model, the cosmic web we analyze, may all be representations shaped by the historical pace of light, rather than absolute reality. In essence, we may be reading a story with a variable narrator, a chronicle, in which the timeline subtly bends and stretches as the messenger travels across the stage. This perspective invites a sense of humility. Our observations, while extraordinarily precise, are mediated, filtered through a fundamental property of nature that we often take for granted. The cosmos, while vast and seemingly knowable, may conceal its true proportions behind the historical behavior of its most ubiquitous traveler, the photon. Consider further the early universe where these effects could be amplified. Light traveling from the first forming galaxies encounters a cosmos dramatically different from today. Space itself was expanding rapidly, matter and radiation interacting with extraordinary intensity. If C varied during these epochs, the mapping of distances to these early galaxies could be substantially altered. Our reconstruction of the timeline of star formation, galaxy evolution, and the assembly of large-scale structures depends critically on precise measurements of light's travel time. Any variation, no matter how subtle, introduces uncertainty. What we perceive as the cosmic history of structure formation may be slightly misaligned with sequences of events occurring earlier or later than reconstructed distances underestimated or overestimated, and velocities miscalculated. The universe's architecture becomes a dynamic tableau, its scale contingent on the historical pace of the photons tracing it across space and time. There is also a deeply personal resonance to this concept, for the distances we measure define the stage upon which all cosmic evolution unfolds, including the conditions necessary for life. Our planet, our solar system, and our galaxy are embedded in this framework, which determines the flow of energy, the formation of elements, and the timeline of events leading to habitability. If the cosmic ruler has subtly shifted over time, the context in which life emerged may be slightly different from our reconstructions. The universe as a cradle for life depends not just on the laws of physics and chemistry, but on the precise dance of light through space pacing, interactions, and informing our models of temporal and spatial progression. Understanding the potential variability of C is therefore not an abstract theoretical exercise, but a consideration that touches the narrative of our own existence, the story of how observers like us emerged to contemplate the cosmos in the first place. The metaphor of light as a flexible measuring tape extends further. Every cosmological distance, from the nearest stars to the most distant quasars, is a function of photons traveling across an expanding, evolving spacetime. If these photons have not traveled at a constant speed, the relationships between objects, the sequence of events, and the inferred chronology of cosmic history are all subtly contingent. The universe we reconstruct may be coherent and intelligible, yet it is also shaped by the historical journey of light, a journey that may have evolved stretching or compressing the space-time narrative like a pliable ruler bending under the Cephin. Unseen forces, even the neat categorization of cosmic epochs, recombination, reionization, galaxy assembly, might carry hidden uncertainties if the messenger of these epochs has shifted its pace during transit. Finally, this concept challenges the confidence we place in cosmological measurements. The elegance of modern astronomy, the precision of instruments like the Hubble Space Telescope, the James Webb Space Telescope, and other observatories rests on the assumption that the speed of light is an absolute constant. If C has varied, every photon arriving at our detectors carries not only information about its source, but also a subtle record of its own historical behavior. In this sense, every observation becomes both revelation and puzzle, a message and a question. Distances, velocities, and timescales are no longer purely observational facts. They are interpretations filtered through the potential malleability of nature's ultimate ruler. As we reflect on this, the philosophical and scientific implications converge. We are observers attempting to measure a cosmos that may be subtly more fluid than we imagine, a universe in which the distances between galaxies, the motion of cosmic structures, and the chronology of events are contingent on the historical journey of light itself. Our instruments and theories are precise, yet they are inevitably mediated, reliant on a property of the universe that may have its own temporal evolution. In contemplating the potential variability of light's speed, we are invited to reconsider not only the scale of the universe, but our place within it, to wonder whether we truly see the cosmos as it exists, or merely perceive a story rendered by the messengers that traverse its vast expanse. The next step in this reflection is intimate and personal, to consider how time itself and the emergence of life are interwoven with the rhythm of light across the universe. Every photon that reaches the Earth from the Sun carries more than just light. It carries time itself. The pace at which light travels dictates the rhythm of physical processes, the unfolding of events, and the progression of life. If the speed of light has been subtly changing over cosmic history, then time as we perceive it on Earth may not be as straightforward as it seems. The flow of seconds, minutes, and hours, the pace of chemical reactions, and even the tempo of biological evolution are all intertwined with the fundamental rhythm of light. Imagine that light is a cosmic metronome, marking the passage of time across the universe. If this metronome has accelerated or decelerated ever so slightly over billions of years, the narrative of life on Earth, its origins, its diversification, its evolutionary milestones could be stretched or compressed, reshaping the story I think we know. The history of our planet, the rise of complex life, and even the emergence of conscious observers may be subtly contingent on the pace of photons traveling through space and time. Consider the role of sunlight in biological and chemical processes. Photosynthesis, the foundation of the Earth's biosphere, depends directly on the arrival of photons from the sunday. If the speed of light were slightly faster in the past, photons would have reached the surface of the planet sooner, potentially altering the timing and efficiency of photosynthetic reactions. Conversely, if light was slower, the energy arriving from the sun would be delayed, subtly affecting the rate of chemical processes that sustain life. Even minor variations in the timing and intensity of incoming light could have cascading effects on climate patterns, ocean currents, and the availability of energy for living organisms. Life on Earth is attuned to a precise rhythm of light, a rhythm that is mirrored in daily, seasonal, and evolutionary cycles. Alterations in the speed of light would ripple through these cycles, changing the cadence of ecological interactions, evolutionary pressures, and the progression of species over time. The concept extends to the perception of geological and biological time. Fossil records, radiometric dating, and molecular clocks rely on assumptions about the constancy of physical laws, including the speed of light. These tools are used to reconstruct the timeline of Earth's history, from the formation of the first continental crust to the rise of complex multicellular organisms and the eventual emergence of humanity. If C were not fixed, the rates of radioactive decay or the propagation of light used in astronomical dating could have shifted subtly, modifying our calculations of ages and durations. The Earth's history, the narrative encoded in rocks, fossils, and isotopes, might then represent a version of events that is already filtered through the changing tempo of light. What we interpret as millions or billions of years may be a reconstructed approximation, a story told not only by the processes themselves, but also by the medium through which we observe them. Beyond chemistry and geology, biological evolution is intimately linked to the pace of time dictated by light. The rhythms of reproduction, mutation, and natural selection unfold in a temporal framework calibrated by energy input from sunlight and by fundamental physical constants. If light has subtly altered its speed, the tempo of evolutionary change could have been different from what we assume. Species may have experienced generations compressed or extended relative to the clock we now impose upon them. The sequence of evolutionary milestones, the emergence of photosynthetic organisms, the Cambrian explosion, the colonization of land, the rise of mammals might have unfolded in a temporal rhythm that differs from our reconstruction, like reading a musical score where the tempo has been adjusted partway through the performance. Life on Earth, in this view, is not merely a product of chemical and genetic processes. but also of the fundamental pace at which photons have delivered energy, information, and causality through time. This raises profound philosophical questions. Are we experiencing reality in a form that is immediate and absolute, or are we immersed in a version of the past, subtly reshaped by the historical pace of light? Every moment, every perception is mediated by photons traveling from one point to another. The now we experience is already filtered, already a reconstruction of events as carried by light. If the speed of light has evolved, then the present itself, the sequence of seconds and the rhythm of time as we know it, may carry traces of this modulation. In essence, we could be inhabiting a version of history that is coherent and continuous, yet subtly edited, a time-lapse of the cosmos and of life that reflects not only events, but also the medium through which they are observed. The implications extend to human consciousness and our perception of causality. Cognitive processes rely on the brain's synchronization with the external environment, which itself is regulated by the timing of light and other signals. If photons from the environment carry a subtly different temporal signature, then we assume the experience of time. The sense of before and after may be contingent on the historical behavior of light. Our subjective sense of duration, the rhythm of life from birth to death, is interwoven with the cosmic metronome. What we perceive as continuous time may, in a broader cosmological context, be a tapestry whose threads are subtly stretched or compressed, where the pace of life itself is entangled with the rhythm of photons that have traversed space for billions of years. Furthermore, the evolution of life and the emergence of consciousness are intertwined with cosmic timescales. The chemical processes that produce the building blocks of life, the assembly of molecules into self-replicating systems, and the development of complex organisms, are all paced events occurring over timescales that assume a constant flow of energy and causality. If light's speed has been variable, the durations of these processes, the timing of key evolutionary innovations, and the coordination of ecological systems may have unfolded differently. The history of life, then, is not just a biological phenomenon, but a chronicle of how energy, information, and light have mediated the passage of time, linking the evolution of species to the dynamics of the cosmos itself. We might imagine the Earth's biosphere as a clockwork mechanism, its gears and springs finely tuned to the cadence of light. And if that cadence has shifted even slightly, the clock would mark hours, days, and millennia, differently altering the Praesic Ritu narrative of life as we reconstruct it. Reflecting on this possibility invites a deeper appreciation of our temporal embeddedness in the universe. We often take for granted that the flow of time is universal, linear, and absolute. Yet if light's speed is mutable, the rhythm of time is intimately connected to the cosmic messenger. The history of life, the development of ecosystems, the rise and fall of species, and the emergence of intelligent observers are all conducted within this temporal framework. What we perceive as linear, consistent, and objective may be a construct contingent on the behavior of photons that have carried information from the sun, from the stars, and from the earliest cosmic epochs. Our experience of past, present, and future is therefore both personal and cosmic, a reflection of the interplay between local processes and the fundamental physics that governs the universe. Ultimately, contemplating the variability of light invites a meditation on the nature of history itself. The chronology of Earth, the progression of life, and the unfolding of evolution are all mapped in relation to the rhythm of light, which may itself carry a subtle signature of change. We are reading a manuscript that has traveled across space and time, edited not only by the processes it describes, but also by the medium through which it is communicated. Every sunrise, every shadow, every photon that illuminates our world is part of this ongoing dialogue between life and the cosmos, between the passage of time and the rhythm of light. If C has been mutable, then our entire conception of temporal reality is enriched, complicated, and transformed, revealing a universe in which life, time, and light are inseparably entwined, each shaping the other across the vast expanse of cosmic history. And so as we contemplate the rhythms of life and the evolution of species under a potentially variable cosmic metronome, we are invited to expand our perspective outward once more, to consider how these intertwined flows of time and energy manifest on a grander scale. The next layer in this reflection moves beyond the personal and the planetary, returning to the universe at large, to the interplay of matter and antimatter, energy and vacuum, and the forces that orchestrate the dynamics of the cosmos itself. The universe in its vastness is a delicate tapestry woven from energy, matter, and the forces that bind them together. Among these, light plays a subtle yet profound role, not merely as an illuminator, but as a regulator of cosmic balance. The speed of light influences the interactions of fundamental particles, the behavior of antimatter, and the dynamics of dark energy. It is intertwined with the very equations that dictate how particles decay, how forces operate, and how energy is distributed across the cosmos. Imagine the universe as a vast, intricately balanced scale, with matter on one side, antimatter on the other, and the tension of light, the speed at which it propagates, acting as the string that keeps the balance from tipping too far in either direction. If C changes even slightly, this tension is altered, subtly influencing the stability and evolution of the cosmos itself. Consider the early universe a seething cauldron of energy, where particles and antiparticles were created in nearly equal numbers. The prevailing theory suggests that for every billion antiparticles, 1,000,000,001 particles were formed, leaving the tiny excess that constitutes all the matter in the observable universe today. The precise outcome of this imbalance depends on the interplay between fundamental constants, reaction rates, and the propagation of information and energy via light. A change in the speed of light could shift the timing of particle interactions, modifying decay rates and altering the residual balance between matter and antimatter. The difference between a universe dominated by matter, capable of forming stars, planets, and life, and one dominated by antimatter, where collisions would annihilate everything, may hinge on this subtle regulation. Light in this sense is not passive, but a crucial participant in the cosmic narrative, its tempo shaping the very conditions that allowed our existence. Beyond the matter-antimatter balance, light also governs the behavior of energy at a fundamental level. Electromagnetic interactions, the forces that bind atoms, drive chemical reactions, and regulate the flow of energy in stars, are all intrinsically connected to C. If light traveled differently in the early universe, the rate at which photons transferred energy, the timing of fusion reactions in the first stars, and even the efficiency of cosmic nucleosynthesis could have been altered. Stars might ignite sooner or later, burn hotter or cooler, and produce different abundances of elements than predicted under the assumption of a constant speed of light. The distribution of hydrogen, helium, and heavier elements, which sets the stage for planet formation and the emergence of life, is intimately tied to this cosmic rhythm. Every photon that journeys through space is part of this dynamic, transmitting energy, regulating forces, and shaping the conditions that allow matter to coalesce into galaxies, stars, and planets. Dark energy, the mysterious force accelerating the expansion of the universe, is similarly influenced by the speed of light as it enters the equations of general relativity and cosmology. The rate at which space itself stretches, the apparent acceleration observed in distant supernovae, and the large-scale geometry of the cosmos are all connected to C. A changing light speed would subtly modulate the expansion rate, affecting the timing of cosmic events, the formation of large-scale structures, and even the eventual fate of the universe. The apparent smoothness of the cosmic expansion could mask underlying variations, suggesting a universe whose evolution is shaped not only by visible matter and energy, but by the historical behavior of light itself. In this sense, light is both the messenger and the mediator, guiding the cosmic balance while carrying information about it across space and time. Philosophically, this scenario invites a new perspective on the nature of reality. We often think of the universe as a static stage governed by fixed laws where matter and energy interact predictably. But if the speed of light is not immutable, The stage itself becomes dynamic, and the actors, the particles, forces, and fields, perform a dance that is subtly modulated by the rhythm of photons. The universe appears stable because the changes in C may be gradual and imperceptible over human timescales. Yet across billions of years, these modulations can shape the grand architecture of galaxies, the distribution of matter, and the persistence of cosmic structures. The balance between energy and matter, the survival of galaxies, and the emergence of complex structures are all contingent on this interplay, hinting at a cosmos that is not merely mechanical, but adaptive, responsive, and sensitive to the pulsarist properties of light. This idea also sheds light on the profound mystery of the fine-tuning of the universe. The precise balance that allows stars to shine, elements to form, and planets to exist seems almost miraculous. If the speed of light has evolved, it may be one of the hidden levers that maintains this balance. Small variations in C could provide the subtle adjustments that keep the cosmic scale from tipping too far, enabling the universe to remain hospitable for matter and life over billions of years. Light becomes more than a physical constant. It becomes a regulator, a stabilizing influence that ensures the persistence of the structures we observe. The universe viewed in this way resembles a living system where fundamental parameters are tuned not once and for all, but modulated over time to sustain balance and coherence. The interplay between light matter and antimatter also emphasizes the interconnectedness of cosmic phenomena. Every change in C affects particle interactions, the formation of elements, the ignition of stars, and the evolution of galaxies. The history of the universe is therefore a record not only of events, but also of the conditions that made those events possible. Light serves as both a chronometer and a regulator, a silent orchestrator whose historical behavior shapes the narrative of cosmic evolution. By observing the universe today, we are reading a story written in photons that have traversed space and time, carrying within them the subtle signatures of balance, tension, and historical modulation. From a broader perspective, the notion that light governs cosmic balance invites speculation about the universe as a living entity. If photons subtly regulate the interactions of matter and energy, maintaining equilibrium across vast scales, then the universe may be more dynamic, responsive, and interconnected than previously imagined. Its evolution is not merely a passive unfolding of initial conditions, but an ongoing process mediated by light, with feedback mechanisms that stabilize structures, maintain balance, and enable the persistence of complexity. The cosmos becomes a system that is both predictable and adaptive, a structure in which fundamental constants, energies, and forces interact in a delicate dance, choreographed by the rhythm of light. This understanding transforms our perception of light from a simple messenger to an active participant in the cosmic narrative. Each photon, whether streaming from a distant star or the cosmic microwave background, carries not only information but also influence, subtly modulating interactions and maintaining balance. The interplay of light matter and antimatter becomes a story of tension and harmony of forces calibrated across unimaginable scales to sustain the universe's structural integrity. It invites us to see the cosmos not as a collection of static objects obeying immutable rules, but as a living system, a dynamic equilibrium in which the properties of light shape the possibilities for matter, energy, and life. As we reflect on this, the mind naturally turns to the question of consciousness and observation. If light has been a regulating force across cosmic history, then the very conditions that allowed life intelligence and the capacity to contemplate the universe are intertwined with its historical behavior. The universe we inhabit, capable of hosting observers like ourselves, may owe its stability, coherence, and richness to the subtle modulation of photons, which have maintained balance-guided structure formation and enabled matter to persist without annihilation. Light, in this view, is not merely a medium for perception but a principle of regulation, a cosmic thread that maintains harmony and coherence throughout the vast expanse of existence. And so, as we consider the role of light in balancing energy, antimatter, and the distribution of matter across the cosmos, we are led to a bold and compelling idea: the universe itself may possess qualities akin to life. It responds, adapts, and maintains equilibrium, with light acting as the guiding influence, a force that breathes coherence into the cosmic fabric. The next step in this exploration is to take this perspective further, to imagine a cosmos not merely as matter and energy in motion, but as a living system pulsating, adapting, and perhaps even breathing in subtle harmony with the rhythm of light itself. Imagine the universe as a living, breathing organism, its vast expanse pulsing with subtle rhythms that govern the behavior of matter, energy, and the passage of time itself. In this vision, light is not merely a messenger, but the heartbeat of the cosmos, its speed dictating the tempo at which cosmic processes unfold. Every photon emitted by distant stars, every quanta of radiation streaming across the void carries with it not only energy and information, but also the rhythm of the universe itself. If the speed of light varies even slightly, then the heartbeat of the cosmos shifts, subtly modulating the timing of star formation, galactic interactions, and the emergence of complex structures. The universe becomes more than a collection of objects obeying rigid physical laws. It becomes a dynamic system synchronized by the rhythm of photons that weave through space and time. Consider the vast web of galaxies, clusters, and filaments that stretch across billions of light years. These structures did not form instantaneously, but evolved over aeons, their interactions guided by gravity and the flow of energy, much of which is carried by light. If C changes, the timing of these interactions is adjusted, altering the sequence in which galaxies merge, clusters coalesce, and stars ignite. The universe's evolution becomes a dynamic dance choreographed by the tempo of light, with each beat influencing the formation of cosmic architecture. It is as though the universe itself breathes its expansions and contractions, its periods of star formation and quiescence responding to the subtle variations in the speed at which information travels across the cosmic stage. We as observers are participants in this rhythm, our understanding of cosmic history entwined with the pulses of photons that have traversed unimaginable distances to reach us. Philosophically, this perspective invites a profound reconsideration of our place within the cosmos. If the universe has its own rhythm, if the flow of time and the evolution of structures are modulated by the heartbeat of light, then we are not merely passive observers, but components of a larger synchrony. Our lives, our perception of time, and even the processes that drive biological and technological evolution are entangled with the cosmic tempo. Moments of clarity, discoveries, and insights occur within this rhythm, echoing the broader cadence of the universe. In this sense, observing the cosmos becomes a form of resonance, a subtle alignment with the dynamic heartbeat that has been pulsing since the first photons escaped the primordial darkness. The idea of a rhythmic universe also reshapes our understanding of causality and temporal order. Processes that we perceive as sequential and linear may be influenced by the underlying tempo of light. The ignition of stars, the collapse of molecular clouds, the merging of galaxies, and the diffusion of energy across cosmic distances could all be slightly modulated by variations in C. This modulation does not violate physical laws, but rather tunes the unfolding of events like a conductor adjusting the tempo of a symphony. The universe becomes a living composition in which energy, matter, and time co-evolve in harmony with the fluctuating rhythm of photons. Our models, which often assume rigid constants and immutable timelines, may capture the broad outlines of this symphony, but miss the subtle tempo variations that give it depth and dynamism. Even the cosmic microwave background, the oldest light we can observe, carries traces of this rhythm. The fluctuations imprinted on this radiation, which inform our understanding of the early universe, may encode subtle information about the tempo at which light propagated during its journey. The formation of the first structures, the recombination of matter and radiation, and the onset of large-scale cosmic evolution could all bear the signature of a universe with a pulsing heartbeat. Each photon arriving at our detectors is a fragment of this rhythm, a message not only of energy and position, but of the tempo that has guided the cosmos across billions of years. By studying these fluctuations, we may learn not only about the distribution of matter and energy, but also about the dynamic cadence that orchestrated their evolution. Moreover, the concept of a living universe extends to the interplay between light, dark energy, and dark matter. These components, which dominate the mass-energy budget of the cosmos, are not passive bystanders. Dark energy drives the accelerated expansion of space, while dark matter shapes the formation of galaxies and clusters. The speed at which light propagates influences the interaction between visible matter and these hidden components, subtly modulating gravitational effects and the propagation of energy. In this sense, light acts as a coordinating force, a universal metronome that maintains coherence across diverse and complex systems. The universe's evolution is not purely mechanical, but dynamically regulated its structures and processes, synchronized by the historical behavior of photons traveling through spacetime. From a human perspective, this rhythmic universe resonates with our own experience of time, perception, and consciousness. We are accustomed to thinking of seconds and minutes as absolute, yet our perception of time is intrinsically tied to the flow of light and energy in our environment. Sunlight regulates circadian rhythms, guides seasonal cycles, and influences biological processes at every level. If the cosmic heartbeat set by the speed of light has shifted over time, then the history of life evolution and consciousness is subtly entwined with these variations. Our awareness of time, our sense of sequence and duration, and even our capacity for reflection are part of a broader cosmic synchrony. We are in essence dancing to the rhythm of photons that have traveled across billions of light years to reach our eyes and minds, participating in the pulse of the universe itself. This perspective also opens the door to imagining extreme possibilities. If the universe has a rhythm, it may have variations, accelerations, or decelerations that are imperceptible on human timescales but consequential over cosmic durations. Cycles of expansion and contraction, periods of intense star formation, followed by quiescence, and the ebb and flow of galactic interactions may all be manifestations of this cosmic tempo. The universe becomes a living, breathing entity, its pulse guiding the emergence and evolution of structures, matter, and life. Observing the cosmos, then, is akin to listening to a symphony whose tempo has been evolving for billions of years, each note carrying the signature of light's historical pace, each melody encoding the rhythm that has shaped everything from the smallest particle to the largest galaxy cluster. Ultimately, contemplating a universe with its own rhythm challenges the way we frame scientific inquiry. We are accustomed to measuring, predicting, and modeling the cosmos under the assumption of fixed constants and immutable laws. Yet, if the heartbeat of light is variable, then our models capture only part of the story, approximating a universe whose dynamics are subtly modulated by the tempo of photons. Our understanding of cosmic history, evolution, and structure is enriched by considering these rhythms, allowing us to perceive the universe not as a static mechanism, but as a living, adaptive, and harmoniously pulsing system. In this vision, we do not merely observe the universe, that we resonate with it. Our insights, discoveries, and even our existence entwined with the rhythm that has orchestrated cosmic evolution since the first light escaped the primordial darkness. As we reflect on this, the mind naturally turns to the extremes of possibility, imagining a cosmos where the modulation of light's speed leads to scenarios that stretch the boundaries of comprehension. These possibilities challenge us to reconsider not only the nature of physical reality, but our role as participants within it. The next step is to venture into these extreme scenarios to explore how the universe might behave under dramatic variations in its cosmic heartbeat, and to contemplate what this could mean for matter, energy, time, and even the potential for conscious life itself. Imagine a universe where the speed of light is not just slightly different but radically altered, perhaps doubled or halved compared to what we measure today. In this scenario, the familiar cosmos we inhabit would be unrecognizable, its very fabric torn and reshaped by the change in the cosmic metronome. Light is not merely an illuminator, it is a structural force governing how matter coalesces, how energy flows, and how time unfolds. If c were dramatically faster, photons would traverse space in an instant, allowing interactions to occur far more rapidly. Stars might ignite almost immediately after matter coalesces, burning intensely for fleeting moments before exhausting their fuel. Galaxies could form and collapse in the blink of an eye, leaving behind a universe that flickers like a strobe of fleeting brilliance. Conversely, if c were drastically slower, light would struggle to mediate interactions across space, delaying fusion in stellar cores, stalling the assembly of galaxies, and extending the gestation of cosmic structures over unimaginably long epochs. The universe would be a sluggish, languid place, its evolution stretched into a tempo almost too slow to perceive, and the stars and galaxies we observe would be mere embryonic sketches barely begun drifting in frozen isolation. This extreme modulation of light speed also affects time itself. Time as experienced by matter and energy is inseparably linked to the rate at which light carries information. In a universe where c doubles causality might accelerate, compressing the duration of events so that processes we consider gradual stellar evolution, chemical reactions, biological timescales would unfold at a vastly increased pace. Civilizations, if they were even possible, under such conditions, might emerge and vanish within cosmic moments, their entire histories flickering across the fabric of time in a compressed whirlwind. In contrast, if c were halved, time would stretch, events elongating across eons, life forms evolving at a glacial pace, stars igniting slowly, and galaxies drifting apart in a languorous, drawn-out ballet. The passage of time would no longer feel linear or predictable. The universe's rhythm, dictated by photons, would redefine what it means to age, to evolve, to exist. The structure of matter itself would be vulnerable under these extreme scenarios. Atomic interactions, chemical bonds, and the forces that stabilize matter rely on the propagation of light to convey electromagnetic influence. A faster c could destabilize these interactions, allowing atoms to form and break apart almost instantaneously, preventing the stable chemistry necessary for stars, planets, and life. Molecules might flicker in and out of existence before they can combine into complex structures, leaving a barren cosmos of transient matter. On the other hand, a slower c would hamper energy transfer, weakening the cohesion of atoms and delaying the interactions that lead to molecular formation. The delicate balance that allows matter to condense to form planets, oceans, and atmospheres could be undone, producing a universe in which the raw materials for life are scattered, inert, or never fully realized. It is a vivid reminder of how precarious the conditions for a stable, life-supporting cosmos are, and how finely tuned the speed of light must be to allow the universe to take the form we know. Cosmic phenomena we take for granted would also transform dramatically. Stars, the engines of element creation, rely on a precise interplay of gravity, pressure, and energy propagation. Alter the speed of light and stellar life cycles shift. Massive stars might collapse too quickly to produce heavier elements or burn too slowly to ignite, leaving a universe dominated by hydrogen and helium with little diversity of matter. Supernovae, which scatter these elements across space to seed new generations of stars and planets, could fail to occur at the right time, halting the cosmic cycle that makes complexity possible. Galaxies might fail to assemble, drifting apart before gravity can bind them, or merging too quickly, creating chaotic, unstable conglomerates. Even black holes, regions defined by light's inability to escape, would behave differently, their event horizons and interactions changing with the tempo of photons. The universe becomes an alien landscape, a theater of extreme physics, where the rules of formation, stability, and survival are rewritten. Philosophically, these extreme scenarios stretch our understanding of what it means for a universe to be possible. If a slight change in c can ripple through the cosmos to produce subtle differences, then extreme changes create entirely alien realities. It forces us to confront the notion of cosmic fragility and contingency. The universe we inhabit, with its stable stars, galaxies, and conditions conducive to life, may be an extraordinary stroke of chance, a delicate balance among countless possibilities. The laws of physics, as we perceive them, may not be absolute but contingent upon precise parameters, including the speed of light, the interplay of forces, the rhythm of cosmic evolution, and the emergence of complex structures all appear to be intimately dependent on this fundamental constant. In contemplating these scenarios, we are reminded that what we consider normal, eternal, or inevitable in the cosmos is in fact a highly specific outcome amid an ocean of potential realities. The mind also struggles with the human perspective in these extreme universes. Could conscious observers exist if light behaved drastically differently? Would life, if it emerged, perceive time, causality, and physical processes in ways that are utterly alien to our understanding? Perhaps consciousness itself, reliant on the flow of information mediated by light, would be impossible under these conditions, leaving a cosmos devoid of sentient witnesses to its unfolding drama. Alternatively, entirely new forms of perception and cognition might arise, attuned to the altered tempo of energy and information, experiencing time, causality, and existence in dimensions incomprehensible to us. This thought challenges the anthropocentric lens through which we usually interpret cosmic phenomena, suggesting that the universe's rules may admit realities far removed from our imagination, where light dictates the rhythm of life in ways we cannot intuitively grasp. Scientific models help us imagine these extremes, yet even simulations reveal the fragility of cosmic stability. Doubling or halving C in theoretical frameworks leads to profound instabilities. Galaxies fail to form stars, collapse prematurely, or fail to ignite. Chemical complexity is curtailed, and the cosmos can fragment into chaotic, inhospitable regions. These models underscore a profound truth. The parameters that govern our universe are finely tuned. The familiar order from planetary orbits to the cycles of stars emerges only within a narrow window of light-speed possibilities. Beyond that, the universe is unrecognizable, a testament to the delicate balance that makes stability, complexity, and ultimately life possible. It compels us to reflect not only on the nature of physical law, but on the contingency inherent in existence itself. This exploration also expands our imagination about cosmic randomness and contingency. Each slight variation in the speed of light, whether subtle or extreme, reshapes the universe's trajectory, suggesting that what we perceive as inevitable may be an artifact of precise conditions rather than an absolute necessity. The cosmos could have been dramatically different, a place where galaxies never stabilized, stars never shone, or time itself moved with alien rhythms. The familiar narrative of cosmic evolution of stars, planets, and life emerging over billions of years appears in this light as one possible story among an almost infinite array of alternate outcomes, each dictated by the underlying tempo of photons traversing space. We are witnessing just one verse in a symphony of potential universes, a song that could have been radically altered with a different beat. Ultimately, considering these extreme scenarios prepares us to confront a deeper philosophical question. How certain can we be about the cosmos we observe? Even within the universe, we inhabit the possibility of subtle variations in fundamental constants, including sea challenges, the assumption that physical laws are fixed and absolute. If light has shifted over cosmic history, the universe we perceive may already be a filtered, edited version of a more complex reality. The extremes where C is radically altered stretch this contemplation to its limits, forcing us to ask whether any observation can provide absolute certainty, or whether we are always reading a cosmos that is contingent, dynamic, and responsive to the rhythms of its fundamental parameters. In this way, the thought experiment of extreme changes in the speed of light is more than a theoretical exercise. It is an invitation to explore the fragile, contingent, and wondrous nature of the universe, to recognize the delicate balance that sustains structure and life, and to confront the philosophical implications of uncertainty. It opens the door to questioning not only what the universe is, but how we know it, and whether our perceptions, measurements, and models can ever fully capture a reality that may be as fluid and dynamic as the cosmic light that shapes it. The next step in this journey is to confront that very question, the limits of our certainty, and the profound humility required to contemplate a cosmos, whose fundamental constants, and thus its very nature, may not be as fixed as we have long assumed. Even as we attempt to grasp the cosmos with the tools of observation, calculation, and imagination, we must acknowledge that there are limits to what light can reveal, and by extension, limits to what we can ever truly know. Light is our primary messenger across space and time, carrying information from distant galaxies, stars, and the primordial glow of the early universe. Yet even with the most advanced telescopes, the sharpest instruments, and the most ingenious experiments, there exists an inherent constraint. The information we receive is mediated by the speed of light, by its historical behavior, and by the fundamental parameters that govern its journey. We are in a sense reading a story that has been filtered, delayed, and modulated, and in that filtering some truths may remain forever inaccessible. Our measurements of the speed of light, of fundamental constants, and of cosmic distances are extraordinarily precise. Yet they are still approximations limited by both the tools we wield and the fundamental properties of the universe itself. Imagine trying to measure the depth and breadth of the ocean with a ruler designed for your desk, each centimeter painstakingly marked. But the scale is minuscule compared to the immensity you seek to understand. The universe is similarly vast, and the speed of light, while foundational, is only a single measure in a sea of variables. Even if we can detect the faintest photons from the most distant corners of space, there may be phenomena that are invisible to light altogether. Events that emit no electromagnetic signature processes that unfold in forms we cannot perceive, or rhythms that occur on scales outside our temporal or spatial resolution. The cosmos may be full of messages, hints, and patterns that our senses and instruments are simply incapable of decoding, and the more we look, the more apparent it becomes that what we see is only a fraction of what is happening. This limitation forces us to confront profound philosophical questions about the nature of knowledge and observation. If there are truths hidden from us, mediated or concealed by the boundaries of light and the speed at which it travels, how confident can we be that our understanding of the universe reflects reality rather than a filtered projection of it? Every theory, every measurement, every model we construct is built upon assumptions that light is reliable, that its speed is constant, and that the laws derived from our local experience hold universally. But if C has changed subtly over cosmic history, if other constants have varied in ways we cannot yet detect, then even our most precise inferences may be incomplete, painting a partial portrait of a far more intricate reality. The universe may not only be dynamic, but also subtly deceptive, revealing enough to sustain curiosity and understanding, yet withholding in ways that challenge the limits of perception and imagination. The philosophical implications extend to our very notion of certainty. Science thrives on evidence reproducibility and the assumption that natural laws are consistent. But the boundaries imposed by the speed of light remind us that certainty is always provisional, contingent on what can be observed and measured. There may be domains forever inaccessible, either because photons cannot reach us from certain regions, because processes occur on scales too large or too small to detect, or because the interplay of variables creates phenomena beyond our comprehension. In this sense, the universe is not a book that can be read in its entirety. It is more like an ancient, vast, and partially illuminated library, with some volumes missing, some pages illegible, and others written in languages we have yet to decipher. We can learn much, yet there is always more to discover, and some mysteries may never yield their secrets. This also invites a humbling reflection on the nature of human cognition and the limits of scientific ambition. Our minds, shaped by evolutionary pressures and local physical conditions, are superbly adapted to navigate and understand the world around us. Yet they may be ill-equipped to fully internalize the vastness, subtlety, and potential variability of cosmic processes. Light, which serves as our primary bridge to the universe, is both a conduit and a constraint. It brings the cosmos to our attention, allowing us to measure distances, infer compositions, and trace the history of galaxies. But it does so according to rules and parameters that may themselves be in flux or limited. Our knowledge is therefore always filtered through layers of mediation: the behavior of light, the design of instruments, and the conceptual frameworks through which we interpret the signals we receive. Even more intriguingly, the universe may deliberately or incidentally conceal its secrets. There may be cosmic phenomena whose signatures are so subtle that they are effectively hidden, intertwined with the statistical noise of the cosmos, or operating in dimensions or modalities beyond light's capacity to carry information. Dark matter, dark energy, the processes in black hole interiors, and the earliest moments of the Big Bang all exemplify aspects of the universe that elude direct observation, forcing reliance on inference modeling and imagination. We construct theories, test predictions, and refine models, yet the full reality might remain forever, out of reach, like a melody that can be sensed, but never entirely heard, or a painting glimpsed through a fogged glass. This perspective instills both humility and wonder, reminding us that knowledge is not absolute, but always an evolving engagement with an expansive, partially concealed reality. The limits of what light can reveal also challenge our assumptions about universality and permanence. Even constants we take as immutable, like the speed of light, may themselves be subject to subtle shifts or variations across space and time. If these shifts exist, they are likely small enough to escape current measurement, yet over cosmic durations their cumulative effect could reshape the structure, evolution, and behavior of the universe. Our observations would then capture only a snapshot, a localized approximation of deeper and more dynamic truths. We may be like sailors mapping a coastline from a single vantage point, unaware of the hidden bays, inlets, and currents that shape the entire seascape. Every measurement, no matter how precise, is an encounter with only a portion of the cosmic reality, filtered through the medium of light and constrained by the limits of human perception and technology. Yet, in acknowledging these limitations, there is a paradoxical opportunity. The very fact that there are boundaries to our knowledge drives curiosity, imagination, and the pursuit of deeper understanding. The unknown becomes a source of wonder rather than despair, prompting us to develop new instruments, new methods, and new conceptual frameworks to probe the unseen. Light may not reveal everything, but it guides us to the edges of comprehension, illuminating what is possible while hinting at what lies beyond. The interplay between revealed knowledge and concealed reality becomes a dance, a creative tension that propels scientific discovery and philosophical reflection alike. Ultimately, the limits imposed by light remind us that the universe may harbor secrets forever beyond our grasp. Not because we lack intelligence or ingenuity, but because the cosmos is vast, dynamic, and subtly veiled. There may be aspects of reality so intricate, processes so delicate, and scales so extreme that photons cannot carry their story, leaving us with glimpses, shadows, and echoes of truths we may never fully decode. This is not a failure of science, but a testament to the grandeur and mystery of existence, an invitation to wonder, to imagine, and to continue the quest for understanding even when certainty is unattainable. In this way, the universe challenges, inspires, and humbles us, offering both knowledge and mystery, and reminding us that the pursuit of understanding is itself a journey illuminated by light, yet always bounded by its fundamental properties. As we stand on the threshold of these reflections, we are compelled to ask, what does it mean to know, and what can light truly tell us about the cosmos? The universe may not only be dynamic and changing, but it may also possess layers of subtlety and concealment that resist our most determined efforts at comprehension. Some secrets may be encoded in the very history of sea, others in phenomena that light cannot carry, and yet others in relationships and interactions beyond the reach of current observation. The cosmos is in this sense an ever-unfolding mystery, revealing enough to spark awe and understanding while simultaneously withholding truths that challenge the limits of human insight. With this awareness, we can turn our gaze outward not only to measure and analyze, but to imagine, dream, and participate in a universe whose vastness and subtlety exceed any measure, reminding us that even as light guides us, it also marks the horizon of what can be known. Light, time, and matter intertwine in a cosmic dance, forming a symphony that is at once precise, mysterious, and profoundly beautiful. Across billions of years and countless light years, the universe pulses with an invisible rhythm where photons traverse the void, guiding interactions, shaping structures, and recording the history of everything from the smallest particle to the largest galaxy cluster. Imagine this symphony not as static notes on a page, but as a living, evolving composition in which the tempo itself, the speed of light, may have subtly changed over time. Every variation, no matter how slight, reverberates through the cosmos, altering the unfolding of events, the formation of structures, and even the perception of time. What we consider fixed, the constants that underpin our physical laws, may instead be threads in a tapestry that shifts with the heartbeat of light. The universe becomes a living canvas, where change is not only possible but woven into the very fabric of reality, and where every photon carries both information and rhythm. Consider the universe as a grand dynamic, painting its composition unfolding across space and time. Light is the brushstroke, drawing the outlines of stars, galaxies, and nebulae with precision and grace. Time is the palette, blending shades and hues that color the flow of events, determining the depth and texture of the cosmic story. Matter forms the patterns, the intricate details that give shape and structure, from planets and moons to the swirling arms of galaxies. If the speed of light has varied even slightly, this painting is not static, it is living, breathing, and responsive. Colors shift, brushstrokes elongate or compress, and the patterns of matter reorganize in subtle, unimaginable ways. The cosmos we see is a snapshot, a momentary glimpse of a vast, evolving artwork, whose final form may never be fully known or understood. This perspective invites both wonder and humility. The physical consequences of a changing speed of light ripple through every aspect of the universe. Distances stretch or shrink, stars shine differently, and the very flow of time warps, reshaping the life cycles of planets, stars, and galaxies. The philosophical implications are equally profound. If light, time, and matter are not fixed but dynamic, then certainty itself becomes a relative concept. Our understanding of the cosmos is built upon observations mediated by light measurements, interpreted through our human perspective, and theories constructed under assumptions that may only hold approximately. We may be witnessing a version of reality that is coherent, beautiful, and logical, yet incomplete. A filtered reality shaped by the rhythm of photons and the limits of perception. In contemplating this, we are confronted with the possibility that the universe is more intricate, more mysterious, and more wondrous than our models or intuition could ever capture. Reflecting on this cosmic interplay also stirs an emotional resonance. There is a profound intimacy in realizing that our perception of time, our experience of change, and even the unfolding of life on Earth are subtly tied to the same forces that govern distant galaxies and primordial light. We are participants in a universal rhythm, resonating with the pulses of energy that have traveled across the void for billions of years to reach us. The dance of light and matter is not only a physical reality, but also a poetic narrative connecting our lives to the vast unfolding story of the cosmos. Every sunrise, every glimmering star, every photon that brushes our retinas is part of this grand composition, reminding us that our existence is woven into the fabric of the universe itself. Yet the universe also retains its mysteries. Even as we grasp the contours of cosmic history, there remain phenomena beyond our current understanding. Dark energy, driving, accelerated expansion, dark matter, shaping the scaffolding of galaxies. The earliest moments of the Big Bang, where classical concepts break down, and the possibility that fundamental constants like C may have shifted over cosmic epochs. These unknowns invite imagination, speculation, and inquiry, extending the canvas of our curiosity beyond what can be measured or observed. The story of the universe is not fully written. It evolves, adapts, and reveals itself gradually, leaving room for wonder and contemplation at every scale. It is a reminder that science and philosophy are intertwined, each offering insight, each revealing new layers of depth, and each acknowledging the profound uncertainty at the heart of existence. In embracing this vision, we also confront the limitations of certainty. While light carries information, it does so within the parameters dictated by its own behavior. Measurements, experiments, and observations are filtered through the medium of photons, and the possibility that their speed or behavior has changed invites reflection on how much of the universe's history we can truly reconstruct. Every calculation from the age of galaxies to the timing of cosmic events is influenced by assumptions about light's constancy. The universe, therefore, is not only vast and dynamic, but also subtle and elusive, revealing itself incrementally and often ambiguously. The cosmos challenges us to balance rigor with imagination, measurement with contemplation, and knowledge, with humility offering both insight and mystery in equal measure. Ultimately, the changing rhythm of light, time, and matter opens the door to endless possibilities, both scientific and philosophical. The universe is a living symphony, a painting in motion, a narrative that unfolds in dimensions beyond our immediate perception. If we allow ourselves to imagine, we begin to see not only the physical consequences, but also the poetic resonance, a cosmos alive, with rhythm, complexity, and interconnectedness. Every photon carries a story, every star contributes a note, and every moment of time participates in an ongoing composition that stretches across space, history, and potential. To ponder the implications of a varying speed of light is to engage with the universe on multiple levels: scientific, philosophical, and emotional, inviting curiosity, reflection, and a sense of awe. And so, as this journey through cosmic possibilities draws to a close, the invitation remains to dream, to imagine, and to remain attuned to the symphony of existence. Light, time, and matter continue their intricate dance, forming a universe that is larger, richer, and more mysterious than our comprehension can fully capture. Pause for a moment to reflect, to feel, to wonder. Let your mind wander across the galaxies, along the paths of photons, and through the tapestry of time. Recognize that while we can study, measure, and theorize, there will always be more to explore, more to imagine, and more to marvel at. In the end, the cosmos is not only a subject of inquiry, but also a source of inspiration, a reminder that the universe is always greater, more intricate, and more beautiful than we can ever imagine. Take a moment to dream the universe is always larger than it appears, and its mysteries invite us to wonder, to ponder, and to continue our journey of discovery.